Yeah, good morning and welcome to this webinar today. My name is Peter, and I'll present the first half, and then Irati will present the second half. For those of you who, if you have a problem with the sound, and then you can't hear me now, but you can look at this slide, and there are some settings under audio and video, and you should go to speaker microphone settings and adjust such that you get the sound properly. And one important thing is, if you want to ask questions, you have to use the Q&A box. So please write in the Q&A box and write to all panelists, and just send your questions during the presentation. We will take a 10 minutes, around 11, where I will answer questions, and then we'll take it in the end, and eventually we can even answer some questions next week. But please write in the Q&A box and write to all panelists. And then we'll collect the questions until after the presentations. All right, then we're ready to start. You can find the slides and the recordings later at the website. And you can mail me and Irati with questions later also. So let's get started. So I'll make an introduction. It's going to be quite brief, but I'll make an introduction to how we can use statistical models for dynamical systems, for data sampled from dynamical systems. So this is the different things we'll go through, but let's just get started, because what we need to think about is that when we want to find, if we want to learn from data, and if we want to find useful models, then we should be really careful, and actually we should make, I really like this saying, everything should be as simple as possible, but not simpler. So we really need to find models which are simple, but of course not too simple, but gives us the right amount of information that we need for a particular application. So which model should we use and how complex it should be? Well, in the statistical approach, then that really depends on data. So you, based on the data, you need to find a good model. And that's what the statistical modeling techniques gives us, that techniques to estimate model parameters and also uncertainty. So how certain do we know these values? And what it also gives us, which is very, very useful, is techniques to verify and argue that we found the best model, or rather, there is no best model. So what we call it is what we can find is a suitable model. So based on the data, we aim to find a suitable model. So we can extract information and draw conclusions from data, and we can of course train models for prediction and use them as basis for optimization. So depending on the application, we can use these the statistical models to fulfill our needs. So then statistical models for dynamical systems, well, we call it time series analysis, and it's been here for many years, and there are tons of literature on this, and it's used for in a lot of applications, controlling airplanes to you name it. Anytime we have time sampled data over time, then what we call a time series, then we basically should use these type of models. So if we want to put them into statistical models into categories, we can say there are a lot of models which are, we could call them static models, so they don't describe dynamics. And then we can, so that's a lot of models we can use for many applications which are not related to time, you can say. So other type of data. but then for dynamical systems, we have a class of models which we call ARMAX models, which are discrete models, which are basically transfer functions, and we'll go through them to see how they are formed, and then we have another type of models which we call gray box models, which are actually formulated in continuous time. So basically, there we can combine physics and statistics in an optimal way. So and that's what we're going to go through and introduce these different type of models. So quickly to give an idea of how they look, well, the static model basically say you have your measurements and they're just a direct function of your inputs plus an error. There's always an error term in a statistical model. So if we extend that, then we can say, instead of just some direct function of that, if that function is actually a transfer function of the inputs, then we would have the first type of model that are useful for discrete or for dynamical systems, with the ARX model, the auto-regressive with exogenous input model. And that works. We can use that for many applications. However, we can actually extend that and also have the error of the model entering through a transfer function. Then we have the ARMAX model, which is actually for linear systems, data from linear systems. This is, in a sense, an optimal model to use, the ARMAX model. So what we call this part is what we call the MA part, the moving average part. And then we have the final type of models, the gray box models, where we actually formulate a state space models. It can be discrete, but when we say gray box, we will think of it as continuous time. So we formulate system equations, and we have state as a state space model. So we have states, and then we have measurement equations where we formulate how the measurements were taken as a function of the states and inputs. And in both cases, we have a description of the error. So that's what we call a gray box model. So we will go through those and see how we can actually use them today or now. And note in all the models, if it's a statistical model, then included in the model is a description of the error. So that is actually what then forms a probability density function, and which makes it a statistical model. So let's work with an example. And let's first, because what makes statistical modeling very strong is that we actually have a whole toolbox to see how well and validate how well the model fits to this particular data. And what we do all the time is that we do what we call model validation, where we examine the residuals. Yes, and what are the residuals? Let's look at this very simple model where we have some model output, which is a linear function of the inputs. So this is the intercept and the slope, and then we have some input variable, and we have the error. So that's the most simple linear regression model which we had in our statistics class in engineering. So and what is this residual? So when we reformulate this a bit, then we say when we actually have the data, then we will put a hat on top of the parameters, which indicate that now we have actually estimates of the parameters. And we have the actual data, so that's what we indicate with the y. It's now small y, and we have estimated. Now we have the values. We have calculated the values of the parameters. And if we take this part, I'll just go back. This part, which is the prediction, if we call that y hat, and if we shift around such that we actually take the observation minus the prediction of the model, then we get what we call the residual. So that's kind of what we say is that it's the observed error. So once we have the data and we fitted the model, we estimated the parameters, then we can calculate the predictions. And if we take the observations minus the predictions, then we get the residual. And which is, we do that all the time. So, and we always want to check two assumptions in these type of models. The first assumption is that the error is normal distributed. So we basically want to check if these residuals that we have, if they more or less follow a normal distribution. That's important if we have few observations, but as soon as we have many observations, let's say more than 30 observations, independent observations, then we don't really have to check this assumption that much. However, we really need to check the second assumption, which is that the error is independent and identically distributed. We call it IID. So we need to check that it's not dependent on other variables and that it's not dependent on other errors in a sense. So, and this is what we'll do all the time. We'll check if the errors, if this assumption is fulfilled. So let's see how that works out with a simple example. Because when we work with time series and when we want to check for this IID and examine the residual, we want to check for if it's like white noise. And white noise means that this is basically, there is no pattern left. And then we use what we call the autocorrelation function, the ACF, to as a statistical measure to check if we have fulfilled or if we have this white noise sequence. So let's take an example. I'll just try to draw something like if we have some simple sequence, some values here. Let's say this is time, and up here we have x. On the y-axis, so some sequence we have sampled. So we sample this with equidistant time. So we have one value of x here at xt, and at that's xt, and at t plus 1 we have another value, and t plus 1 and t plus 2 have yet another value. And now if I want to draw this, which I call white noise, I need to make this completely random each time. Each new point is not dependent on any of the other points. And that's what we call white noise. And how do we examine that? Well, we calculate what is called the autocorrelation function. And what happens is that we take the sequence, and now I just make up some numbers. And then we shift that sequence one step. So we lag it. We say that we lag the sequence, and then we just shift it one time step. So we get values like this. And if we plot these values versus each other, xt minus 1 and xt, then we will get some scatter plot. And in the case where these values are independent of each other, then we'll just get some kind of, we can't see really a pattern here. And if we calculate the correlation between xt and xt minus 1, I can write xt minus lag here, then in this case we'll have more or less something like 0. So this is what is used to form the autocorrelation function. And the autocorrelation function takes the lag, so how much did we shift this series, and then plots the correlation between xt and xt lagged with this lag. So at lag 1, we might have some here. It's not really a high correlation. We also include like 0, which is always 1. If we have xt versus xt, it will be on a straight line, so the correlation is exactly 1. And then we take the correlation for lag 2, lag 3, and what we'll get, if we have white noise, so they are independent. If we lag the sequence and we look at this, then it's independent, so there will be only a small correlation, and we can make a confidence interval, 95% confidence interval, and then only 5% of these correlations will stick out of this. And that's what we use the autocorrelation function to identify for sequences white noise. So if we look at this in R, we can generate just random numbers I just generate a sequence of random numbers, and if I plot it, it looks like this, and we can see there's not really any pattern. And we can see that the autocorrelation of this, yeah, well, most of these correlations, they are inside this confidence interval. So we can look at the autocorrelation, and we can say this. We cannot say it's different from white noise. So we can conclude this is probably white noise. So what if it's not white noise? What would we have? Now we would have some kind of sequence where if now it's actually moving around like this in some pattern. And if we do the scatter plot of xt minus 1 and xt here, then we will see, oh, when the value is high, then the previous value was also high, and when it's low, the previous value was also in like the lower range. So we'll get something like this. And the autocorrelation will look like this. We'll have some kind of pattern like this in this case. So clearly sticking out, these bars will stick out of the confidence interval. So when we look at it here, now I take some white noise and I put it through a filter, so I get this moving pattern. And then when I calculate the autocorrelation of this, I can clearly see there's a pattern here. So many of these bars, way too many are sticking out of this blue confidence interval. So we can, by calculating the autocorrelation, we can say that this is not white noise. Right, so now we introduce white noise and the autocorrelation, and we can see how to use that by making some simple example. Because that's what we're going to use when we fit models to data. Then we want to validate the model, and we want to check. We want to analyze the residuals, and we want to check if they are white noise. If they're white noise, we're happy. If they are not white noise, well, then we know we can still improve the model. We still need to describe some pattern in the data if we don't have white noise left. If the residuals are not white noise, then we know we have to do something to improve the model. And that's a really strong tool, because that makes us not just modeling blinded, and we can actually find out how to find a good model for this particular data. So let's take an example. If we make the simplest linear system, kind of a very simple building, we have the internal temperature. Let's think of the internal temperature, and we have some envelope here, and well, there's some thermal capacity, so some capacity in this building, and we say that this envelope, there's a resistance to the external temperature, and the external temperature is driving the system, so it's actually like a voltage. So this is an RC diagram, so it's equivalent to voltages, but that's and current. So yeah, so when it's a linear system, this can be completely characterized with such an RC diagram. And so this would be the simplest first order model that we can come up with. And if we can actually model from physics, we know that what will happen if the external temperature change, then we can predict, we can simulate what will happen to the internal temperature. And we can do that with this ordinary differential equation. So we also learn about that in engineering school. So the change of the internal temperature as a function of the internal temperature and the external temperature looks like this. So it goes, and this is a first order system, and it's basically what we call a low pass filter. So when we actually simulate this, then what will happen is that the black line here is the external temperature, and there will be some inertia in the system. So the internal temperature will be sort of a smooth low pass filter version of this external temperature. So simulating this, with the external temperature starting and the internal temperature starting here, then the internal temperature, the model say it will evolve like this. So if we have this and if we add a bit of noise, there will always be noise on real data. So we add a bit of noise, measurement noise, just added on top of this. The blue line just added some white noise on top of that. Then we have some simple data which we can work with. So let's try to fit some models to that data. Let's first try with a simple linear regression model. So the simplest model we can come up with, it's a static model, we can call it. So we're not describing any dynamics. And with this model, we just say the internal temperature measured at time t, it's just directly a function of it's just directly at this instantaneously change with the external temperature. Just multiply it with some coefficient. So if we take the data and actually estimate this coefficient, then we with least square linear regression, so it's least squares, and we get the value of omega e here, and then we can make the predictions using that model, and that's going to be the blue line here. And it looks, well, not super nice when we compare it to the red line. So we can already see, of course, this model is not really super good because it's not really predicting the red line very well. So what can we do? Yes, of course, we want to check the residuals. And the residuals are simply the observation. In this case, it's the red, which we generated the data ourselves, but that's the observations, minus the prediction. So this is a residual at this point in time. So it's this difference. So if we calculate these residuals, they look like this. And now we want to check if they are IID. So are they independent? We could check if they are independent of other variables, but now we're going to check if they are independent of themselves, you can say, if the inherent structure is independent in this sequence. And so we're checking if this sequence is white noise, and we can already see it's not. There is a pattern left, of course. So just by looking at the sequence, we can say, but we want to use the autocorrelation function to make it a little bit more concise. So when we calculate the autocorrelation function of this, we can see, it's not white noise. It's not a good model. We can improve it. So we can think of a way, how do we find a better model? So let's go back to now we know how this system works. It works like this. So let's look at how we can actually make a good model for this. What we know also from engineering school is that maybe we forgot it. Then we can look it up. But I tend to forget things. But then that's great. We can look it up. And then what I did when I looked it up in my math book, I realized, oh yeah, it was page 1 more or less of my engineering math book, how to solve such a differential equation. Oh, sorry. And the solution ahead in time. So if we know the temperature at time t, and if we have the external temperature, then ahead in time, the system, delta t, a time step of delta t ahead in time, the internal temperature will look at this. So it's a solution to this ordinary differential equation. And if we move a little bit around this, then and if we say that the sampling frequency is, or we normalize such that delta t is 1, so it could be 1 hour, whatever, and we say that the external temperature is constant between the sample points, then we end up with this solution. So the next observation, our prediction of our prediction with this model of the next value in the time series will be like this. And there we see that now we actually have it's a linear model in the current value of the internal temperature and the external temperature multiplied with these two. And actually, this one we know is a negative value, so it's between 0 and 1. This part is negative, so taking the exponential of that makes it between 0 and 1. And thus we can write this model in this way, where we know these two parameters are actually between 0 and 1. And now we have what is actually, if we add an error to this model, then we actually have the ARX model. So now we have found out that if it's a linear system for order 1, then we should exactly use this ARX model to model this. And it says, take the current value times multiply this with a coefficient and take the current value of the external temperature of the input and multiply it with a coefficient. Then that's a prediction of the next time step of the internal temperature, which is our model input now. We just do a small trick because then we can write it up like this. That's how we usually do it. We just, instead of making +1, we shift the time step of all the variables such that we say the current value is a function of the previous values. And then we have the ARX model. So let's try that on the data. So we formulate the model like this, and it's a discrete model because it's just simply taking the sequence here and then using the sequence lagged one step and using it as an input. And actually, this is simply just a linear regression model. So we can just fit this with the least squares and get the values of the coefficients. And if we do that, then we obtain these blue predictions, which is at least much better than the previous model. So yeah, okay, it looks kind of fine. We found some good a good model, and we can predict the internal temperature quite well. Or we only predict one step ahead, but it looks kind of fine. And we can look at the residuals and say, yeah, they look like white noise. That's pretty fine. And but let's look at the autocorrelation, and it looks kind of good. Looks very close to white noise. However, there's actually still one lag here, which seems to be a little bit like one is a little bit too much autocorrelation correlation. So we miss a little bit. We miss actually the MA part. In order to have the best model, then we need to add an MA part to this model. So we do that by adding this part where we actually take the last error we had and also include that as an input to the model. And if we do that and fit the model, now it's a little bit more complicated to fit the model, and we actually need a Kalman filter to do this. Then what we get is this, the prediction is this blue smooth line, and now we actually really separated the noise from the actual let's say state itself, or the internal temperature itself. So that's what the Kalman filter, that's why it's called a filter, because it separates the noise and the signal. But now we found we improved the model, and we think we did, but let's investigate the residuals. And now the residuals, the autocorrelation function of the residuals looks really nice, and we have actually just, we cannot say that it's not white noise. So we cannot reject the hypothesis. The residuals are white noise. Now the hypothesis should be that now my brain gets a little bit confused. That's what happens all the time with this. But if we set up the null hypothesis, this is not white noise, and we get this, then we can then we can reject that, and we have actually statistical evidence that this is white noise. So we're happy, and we want to use this model. We say we cannot improve it further. Yes. So that's how we want. That's a technique of finding models for data sample from dynamical systems using statistical models. And we are always doing this. We're validating the one-step prediction residuals, and we can shift the time steps such that we say the residual at time t is the observation at time t minus the prediction made at last time point. That's how we write this. So now we have techniques to find models, and we are using until now discrete time models, and in classical time series analysis with discrete models, that's what I mean. We generalize this, and we say that we have auto-regressive models. They look like this. where there's no other inputs than the series itself. We have ARX models, that's where we have another input variable, and we have ARMAX models where we have also the MA part. And we have the same assumptions that the error is normal distributed. Less important if we have many observations, but very importantly that the errors are IID, so identically independent distributed. That's why we check for white noise. And if we have white noise, then we can also trust the statistical measures. At least if we did not use a too complicated model. But if we start with a simple model and we extend it in steps, then we can end up with the model which we say now we cannot improve it any further, and then we say we have the suitable model. All right, and we can generalize this. Okay, just a slide saying that some notations it's X that's the input, or sometimes it's a U that's the input of the models, just notation wise. I know this is very fast. I speak very fast, so of course. But I hope that if you want to go back, you can do that when you get the video, and you can review some of this. But I have to keep within the time. So, and maybe it would be natural now to take some questions, but we'll look at that once we get to the end. So, drink some more coffee and follow on. I hope it's fine. Yeah, I don't hear anything from you, so I'm just talking to my computer. But all right, let's go on. Yeah, so if we want to generalize it even more, we can say this was of order 1, so we had only lag 1 in the models, but we can generalize it to say this is modeling systems of order P, and then we would have P lags in the model, up to P lags in the model. Well, we don't need to have the same order for all the parts, but this is a generalized way of writing it. And what it means is basically that if we have more complicated, if we have a system with a second order system, something like this with two C's and 2 R's, then we need an order of 2. Then we will model this system optimally. So linear systems and the order of the model are directly related to each other. And we can even generalize it even more. So we would write it in a way where we use this what we call the backshift operator. So and that means we can then write the notation even more concise, such that we write these polynomials in the backshift operator. And we can write the models even more concise. And actually, if you start investigating the properties of these models, then you write it like this, and then the properties of these polynomials make these different models have, or depending on the parameters, there's different characteristics of the models and so forth. But doing it like this, then it also allows us to see that this is actually what we're modeling is actually transfer function models. So by taking this part, the phi, the AR polynomial, and dividing it on each term here on the other side, then we can see that this is what we call, or this is what is known as a transfer function. So if you work with designing electrical circuits, that's the first thing to get introduced to, is how to design a transfer function of some circuit of electrical components, or like basic electrical components. So, but that's the type of models, or if we sample data from such that has been through such systems, then that's exactly what we can model with these type of models. All right, so that was, and of course we need different implementations, techniques to estimate the parameters. And in R, I mean, there are MATLAB, there are Python, there are many different languages, but in R, you have all of these. I mean, you have them in MATLAB and Python and so forth. The ARX model is basically a linear regression model, so you can use any linear regression implementation. In R, the basic one is called LM function. R has a function called ARIMA where you can fit ARMA models and also actually have the I. The I is standing for integration and different things, so you can do that with the ARIMA function, but it has some problems when you want to include external variables. So there you have to actually, to do it the right way, you have to use some other packages, one called Marima, which an old guy from DTU did, or there are other packages which you can search and find. So, and they are all free and available in R. And what we need to remember is now, when in the classical time series analysis, these are all linear models of linear systems, but they can be tweaked to make nonlinear models in many ways. So even neural networks can be set up to be these recurrent neural networks, and you can you can model nonlinear systems in this way. All right. So that completes the discrete modeling. Now we will and the white noise and how we validate the model and how we check the residuals and how we see if we can improve the models. So if we step into the gray box modeling and also the package which in our package which we have made at DTU for many years. Let's go to that. So now we introduce the gray box models and how to use the CTSM-R. Yeah, CTSM stands for Continuous Time Stochastic Modeling in R. So that's the R in the name. I mean, one can say, to be more correct, let's say it's called Continuous Discrete Time Models because some part of the model is continuous, another part is discrete. But let's look at that. I mean, why do we call it gray box models? That's because one way to talk about these things is that a white box model is deterministic equations. So from physical knowledge, you will basically say the R and C values have this or whatever kind of physical system you model, and then you set the parameters and you simulate how the system will work. If let's say we had, on the other hand, a black box model, one could say that the discrete time models are black box models because the parameters in those models don't have a direct physical interpretation. The gray box models are in between, so that's where we actually use the physical models and physical knowledge. So we formulate the models based on this, and then we integrate that with data, such that we're able to fit the models from and basically combine the physical knowledge with the statistical techniques. Yeah, so we bridge the gap between physics and statistics, and you can find a manual on the website. I can just quickly go and show the website. So it's ctsm.info, and you can look up how to install the package. You need some additional compilers if you're on Windows and Mac, but they are just wrapped in what is called R tools. And there's documentation, there's a manual, and some different examples. And there's also some extra material, to show you some extra tricks that you can do. And also this small little example where you simulate, where you just basically start. Yeah, that's a good starting point to look at this simulation example. Yes, so you found the information there, and of course in the articles that has been written and where the package has been applied, you can look those up. We'll provide you with a list of literature. All right. So how do these models look like? Basically, it's a state space model. So you want to define first a set of actually stochastic differential equations, but it's basically your knowledge from physics from differential equations is written in this part, and then combined with a model for the error that enters through the system. One can say it doesn't have to be that complicated, but that's what you can do. You can combine that. We'll see in an example how that looks. And then that's what we call the system equations. You combine, then you also have to define the measurement equations, which basically describe how the measurements were taken as a function of the states. So yeah, the states model how your system evolved over time, and then you say, how did we actually take the measurements of the system? Well, that's a function of the states and inputs and time. You can define this function. And then there's a measurement error. So every time you take a measurement, there will be some error in the whatever sensor you have, and that's characterized by this the measurement error, which is a normal distributed, assumed normal distributed, and so forth. So yeah, the physics you define in the up here in the system equation, and how the measurements were taken is defined here in the observation equation. All right, so let's look at this. Let's take the same example and write up a model for this. So now we know that we generated the data like this. So what we will write is that we'll just take this model and write it directly into the system equation. The only thing that we'll add is this part, which we call, over here we call it the state. And this part, some more or less just a differential equation, which we know from physics, times dt, is called the drift term. And this part, which is multiplied by this, which is called the Wiener process, is called the diffusion term. And in this case, we just have one parameter, which then sets the scaling of this diffusion term. Okay, but that's basically just taking our knowledge of the system from physics and writing it here, and then adding this diffusion term. And in the measurement equation, well, over here is the observation, and this, now we just simply enter the state. So what we observe here is actually the state of the model, but there could be multiple states, and we only observe one of them, for example. Or we can observe a function of the states. We can write that down here. And then we have the measurement error. So this is how we would formulate, and those two equations would then form a gray box model. And we have the assumption of normal distribution and IID on this error. So, and that's what we can check. We'll calculate residual as one step ahead residuals, and we'll check this assumption again. So let's see how it works out. Oops, there's one problem actually, because when we write up a model like this, it's actually what we call unidentifiable, because you can actually, in this very, very simple case, you can actually see it that basically, if you change R and C in this model, if you change R, you can change C, and you get exactly the same prediction. So we cannot separate these two parameters. So what we have to do is actually just to estimate them as a single parameter, which is then the time constant of the system directly. And it's the same for the discrete models. We couldn't estimate the R and C separately. Yeah, so it's an important point to think to, and we're working on that, how to check the models if they are identifiable. All right, so now we'll try with this model to fit it to data, and we will write it we'll use this package CTSM-R, and we will write it in R like this. We load the package, and then we get this class, which is called CTSM. And then we can have an object of that class, and then we have functions where we can define the model equations. And we can say, then we need to say which of these variables up here were actually inputs. And we need to add the observation equation. We do like this. And then the measurement error, how we do that. So with this in the package, we have a class which has different functions for actually defining the model. So now doing this, then we have actually defined the model, and then what we need to do, we'll come back to that in just a second. Now we need to estimate the parameters in the model, and in this case there are basically three parameters in the model. There's the time constant, and there are the two standard deviations of the errors. And then there's also the initial value of the states are estimated. And in order to carry out the estimation, then we need to give it an initial value and we will use an optimizer to find the best values, the best parameters. The optimizer needs some initial values and needs some lower and upper bounds for the optimization. So we need to set that for all the parameters to be estimated, and then once we've done that, then we can use a function called estimate on the object, and then we have to provide the data in X as a data frame in R, and then we get the result returned by this function. And eventually we can take the one-step predictions, and we can do like this, and then we get the residuals from the gray box model. So exactly the same as we did with the discrete models before, and now we calculate the autocorrelation function of these residuals, and we can see, yes, they look like white noise. And actually, when we examine the prediction, we can look at the prediction from the ARMAX model that we did and the gray box model, and we can see they are very, very close together, and they are actually equivalent. It is just a matter of there are some small differences essentially, but they're very, very similar. So they get more or less the same results when we estimate them to this simple example, because they are more or less equivalent. It's just the way the parameters are estimated that are slightly different. So if we look at the residuals from the ARMAX and the gray box, they're very, very similar. So they are actually equivalent, these techniques, and that's a nice thing that building the continuous time models is building on top of this classical or the time series analysis that we have used for many, many years also. So that's really nice. Okay, I see time is kind of running out. I have 8 minutes left and 8 slides left, so it's going to be a little bit quick, the last part. It's been quick already, I know, but just to give you quickly an idea about how the parameters are estimated, then they are estimated by what we call likelihood technique, and what we do is that we calculate the maximum likelihood, and it's written up like this in math. So basically, we take the observations and we take a model. If we have a very simple model with just 2 parameters, then we say what's actually the joint likelihood, the joint probability function of observing this data given the model and these parameters. I can quickly give an idea how this works. So basically, we could have, now we just say we have some observations, they follow a normal distribution. It's a very, very simple model. So maybe it could be this normal distribution. So we have one mean and one standard deviation. And now we say with this particular mean and this particular standard deviation, this is how the model the statistical model will predict the data. And we have the data, so maybe the data was here. Maybe this is the values in our sample. We have 5 observations, and to calculate the likelihood is very simple. If we assume they are independent, then basically what we do is that we just look up the value of this probability density function and multiply those values together. So this value multiplied with this value with this value. All right, then we get the likelihood. It has a certain value. Now what we can do is that we can change the 2 parameters in the model, and maybe we can change them such that the model is here. Okay, that was really poorly drawn. Maybe we can change the value such that the model predicts here, so it's another value of the parameters. It's the same model, but other values of the parameters. And now we calculate the likelihood again, and now we have actually higher values. So this model, with these parameters, it fits better. So now we get higher values, so the likelihood will be higher. And that's what we're going to do. We're going to find the parameters in the model which which maximize this likelihood function. And then we have one challenge, that is how to do. So what we do is that we find the values of the parameters which maximize this likelihood function. And then that's what we call maximum likelihood estimates of the parameters. And if we do that, then that's really cool. We have a whole theory that gives us a lot of all the statistical results, all the statistical methods that we need to get the uncertainty and to select models and stuff. That's what we get if we're able to do this this maximum likelihood estimation. Yeah, one particular detail is we always use we actually, due to numerical reasons, we minimize the negative log likelihood, but you don't have to think about that right now. Yes, so then our problem is that now we have the time series data, so we have data sampled over time. And how do we calculate the likelihood for that? Well, again, actually, now I know it's very complicated, it's way too fast, I'm explaining this, but essentially this part, the probability density function that we're using is the PDF of the one-step ahead predictions. And if we assume IID of the error, that the errors are independent, then basically, and we assume that we have a normal distribution, then we can calculate the likelihood like this, where all we need to do is calculate these one-step ahead predictions, and they need to be independent. Then we're able to calculate the likelihood. Then it's the likelihood of this. And then if they are independent, the assumptions are fulfilled, then all the statistical results we get out in the end we can trust those. All right, that was very fast, but and how do we calculate these for these continuous time models? Well, we use the Kalman filter. I won't go into details of this. We could spend a whole hour on that. But the Kalman filter is exactly what we need to solve this. To solve these state space models and to calculate the predictions. So basically, when you want to apply one of these, the gray box models, and do maximum likelihood, what you need to first load the data. You need to define a model. You need to define the initial values and parameter bounds. Then you need to run an optimizer to find the parameters which maximize the likelihood. So you run the prediction, the Kalman filter, many times with different values of the parameters until we maximize the likelihood. And then we want to interpret and validate the results. And first we need to check if the optimizer converged. And we need to check that no parameters hit the boundaries. And after that, we can check the estimated results and the statistics, and we need to validate the model by analyzing the residuals to check if it's white noise. So now I'll just quickly, I will not spend. I have one example, which is the example that's on the website, so you can go and download this. So it basically takes some data that we observed in a building. So you can see here the heater was switched on and off, and then the internal temperature were changing. And so that's kind of simple data in the sense that we just really pushed the system with the heater and the internal temperature changed in the building. And now we want to fit models to that. So we use CTSM-R and we define linear models, a simple linear model, and then we define these different things, and then we run the estimation. It takes a bit of, it just needs to start. I don't know why it waits a bit here, but actually what we'll see in a second when it's running, I'm not sure why it's actually what it's doing here. It will run very soon. But once we run the result, we will check the result, and actually what we'll see is that we need to do a bit of checking of the result, and then we'll be able to now it runs. I have no idea why it waits so long. Now we've run it again. It's very fast. Now we can check the result, and what we first need to check is these convergence results, and we need to check these columns. And we don't want high values here. These have to be low compared to each other. And actually what we learn is that this parameter R needs a lower bound. It ended up at 10, which is the lower bound here in the optimization, so we need to change that to 1. So we run that again and we do the estimation. And now it's fine. These values are very small. And so basically now we can look up the estimates of the parameters here, and we can look at the standard error estimated. So if we want a confidence interval for these parameters, it's more or less 2 times these values, and we can see if they are the standard usual t-test for parameters. So yeah, and we can calculate the residuals, and we will calculate the now I have this box. We'll calculate the autocorrelation. We can see it's not white noise. This was a too simple model, and we need to improve the model. And basically, you can, I'll send you the paper where we then develop the models and make it work out. So we can look at residuals, and we can see there's still a pattern in the residuals up here. So we need to really do something about the model and improve it. So I have 2 slides left. So the real difficult thing of all this is actually to find the model which has the proper, of course, the right model, but also the model that has that is not too simple and not too complicated. And what we basically need to do, or we need to find some strategy to find the model. And usually what we do is that we start here, it says model complexity here. We start with a simple model, and then we increase the complexity until we find the point where now we're not really improving the model if we add more complexity. And that's where we have different techniques to do that. We have different tests. We have, for example, the likelihood ratio test, which we can use with the gray box models, and there are some examples of that on the website. And basically, we need some strategies, and usually, I think the forward selection strategy is the best, where we start with a simple model and we extend it to make it more complicated until we get the white noise, and then we say now we have the best model, or a suitable model. All right, so basically, I mean, you can check if you want to work with this, you should check the website and you should install the package and try some of these examples, and hopefully you can then get started. And Rita will now explain how it can be applied to model this data from the box. So I'll stop here, and I know this was probably way too fast and way too many details, but I hope that it gives you an impression of that these techniques are really, really strong, and they are really, they really give you a lot of techniques to find good models and to understand why one model is better than another model, and to maneuver in this, when working with data and modeling, you get the techniques you need to understand what is a good model and what is a bad model, and you get the techniques to identify a good model. And to learn what's happening with this data. Why is this model good? Why is it not good? How should we extend the model? Usually, you make a simple model and then you fit it to the data and you look at, oh, here in this part it works nice, but over here it's not nice, by looking at the residuals. And then over here, that's where you have the solar radiation. So we need to improve the part in the model with the solar radiation, for example.